subject of study is inverse and composite functions. First, we're going to take a look at inverse functions, and I'm going to read to you right out of the book at the very beginning of the second section. When we go from an output of a function back to its inputs, we get an inverse relation. Now, I want to give you an example of that. If I were in Germany, and mind you, there's equations involved. If I knew that I wore a size 9 shoe in the United States, I'd have to convert that to a size, I'm not sure what it is, maybe a 38, a European size 38. Well, if I were to take that European size 38 and convert it back, because maybe now I'm a German and I've come to the United States and I want to take the size 9 in the American and get it back to my German size, that's the concept of when we go from an output of a function back to its inputs. So we may look at the conversion going from English to German size, if you will, and then backwards again. And what we're doing is we're switching the values of the ordered pairs. When that relation is a function, in other words, for every input we have only one output, we have what's called an inverse function. We're going to study inverse functions and how to find formulas when the original function has a formula. We're going to try to find its inverse. All I want to do with you now is to take a look at some ordered pairs and look at their inverses. So first of all, if I were to graph these ordered pairs, here's the first, here's the second, and here's the third. The inverse of these ordered pairs, I just switched the x and the y values. So I'd have here, instead of 0, 1, I'd have 1, 0. And so that point is right here. Again, here's the original ordered pair. Here's its inverse. The next one, I have 1, 3. Its inverse is 3, 1. So I'm over here and right here. So if that's the original ordered pair, here's its inverse. And then 2, 5. Its inverse is 5, 2, which is right here. So here's the original ordered pair. Here's its inverse. Here's the graph of the original function. Here is the graph of the inverse function. And again, I alluded to this in the previous section. If you drew a dotted line right through the origin and where it bisected the first quadrant and the third quadrant, that line right here is called y equals x. A function and its inverse should be reflected across that y equals x. And it's because we switched the values of the ordered pairs. Where x was 0 and y was 1 here, now x is 1 and y is 0. That is the definition of an inverse. Now all I would like to do is to graph a function and its inverse, and again see if it has that reflective property. So here's a function, y equals 2x plus 3. So I'm just going to pick the values of a negative 1, 0, and 1 to put into that equation. And when I do, 2 times the negative 1, when I put this value in as a negative 2, add 3 to it, I get 1 out. 2 times 0 is nothing, plus 3 is 3. And then I put a 1 in there, 2 times 1 is 2, plus 3 is 5. So I graph this function, and here's my first order pair, where x is a negative 1, y is 1. X is 0, y is 3, and x is 1, y is 5. So there is the graph. Supposed to hit the dots there, but there is the graph of this function. Its inverse is, all I do is I switch the x and the y values. So I would come up here and I would say x equals 2y plus 3. And then I would graph that using a table of values, and because y is on the right side with the other terms, I'm going to pick values for y this time, like a negative 1, 0, and 1. I'm going to put those in for y, so 2 times a negative 1 is a negative 2, add 3 to that, I get 1 out. 2 times nothing is nothing, plus 3. 2 times 1 is 2, plus 3 is 5, and I go to plot these. When x is 1, y is 3. I'm sorry, I wasn't reading that right. When x is 1, y is a negative 1. There's my first order pair. When x is 3, y is 0. And when x is 5, I'm trying to decide if I plotted these points wrong. I have. I plotted this very first point wrong. Again, x is 1, y is a negative 1. That's the inverse function, or inverse point to that. When x is 3, y is 0. It's the inverse point to that. And when x is 5, y is 1. Here's the inverse to that point. And when I sketch a line through that, I have the graph of the inverse, and I can also see that all of this is a reflection over that line where y is equal to x. So I can see that I have done a nice job of graphing the inverse function because I have a reflection over that y equals x axis. Let's graph this function, and let's graph its inverse, and let's see if we feel that we do have an inverse once we have done that. So y equals 3x squared plus 2. When I put these values in for x, and I square them, multiply them by 3, and then subtract 2 from them. For example, I'm just going to do one of them. A negative 2 squared is 4. 4 times 3 is 12. 12 plus 2 is 14. When I put a negative 1 in here for x, a negative 1 squared is a positive 1 times 3 is 3. 3 plus 2 is 5. When I put in a 0, I have nothing there. When I put in a 1, I'll get a 5 back out. When I put in a 2, I'll get a 14 back out. I'm not going to be able to graph this whole thing. I've only got up to 10 on the y-axis, so I'm just going to estimate that 14 is up here somewhere. A negative 1, I've got 1, 2, 3, 4, 5. When x is 0, y is 2. X is 1, y is 5. X is 2, y is way up here at 14. So I have a parabola. I knew that. I have an x squared equation, and it looks like that. Now, its inverse is a matter of swapping these values. So where y is, I'll put an x, and where x is, I'll put a y. And so now what I'm going to do is I'm going to pick these values for y. Now, I don't have to go through this calculation again because I did it over there, and I'm going to find out that when I put in a negative 2 for y, I'm going to get 14. And when I put in a negative 1, I'll get 5. And when I put in 0, I'll get 2. And then 5, and then 14 again. And let's plot these ordered pairs. Again, like the last one, when x is 14, I'm way out here somewhere, and y is a negative 2. So, you know, I'm right about here. This point right here, where x is 5 and y is a negative 1 is right there. When x is 2, y is 0. When x is 5, y is 1. And when x is 14, y is 2. So a point way out here. And I have something like this, a parabola again, going through those points. And all I'm wondering is if I've graphed a function that if I folded the paper right here, and this had ink on it, that I would get a reflection over there. And I have, so I have an inverse function. I've graphed a function and its inverse, and that's what I was looking to do. This is still the graph of the previous problem. Y equals 3x squared plus 2 right here, and its inverse relation. What I would like to discuss now is whether or not the graph of the inverse is indeed a function. And if you would remember, the definition of a function, or one way to state the definition of a function, is for every input there is a single output. And we've said that if a graph is a function, that it should pass the vertical line test. Well, this graph right here, this parabola, passes the vertical line test. No problem. It is a function. But this right here, its inverse, when I draw vertical lines through it, it does not pass the vertical line test because for a single input, I get two outputs. No longer a function, a relation. All right? So what we're going to ask you to do in future problems now is to graph a function, and if it truly is a function, it passes the vertical line test. But what we care about then is, does it pass a horizontal line test, so that here it would pass a vertical line test, and we could say that the graph of its inverse is a function. And if that's the case, we call it a one-to-one. A function that has an inverse is a one-to-one relationship. Again, we can state that both are functions. They have to pass the vertical line test here and the horizontal line test in order to pass the vertical test here as well. My goal with the next problem is to determine if this function has a one-to-one relationship with its inverse. So what I need to do, and all I really need to do, is to graph the function itself and see if it passes the horizontal line test. So what I'm going to do is I'm going to pick values of 0, 1, and 2 to put into the function, and then find out what its output is. So when I put a 0 in here, 3 minus nothing is 3. And when I put a 1 in there, 6 times 1 is 6. 3 minus 6 is a negative 3. And when I put a 2 in there, that'll be a 12. 3 minus 12, negative 9. So I go to graph this. And when x is 0, y is 3. There's that ordered pair. When x is 1, y is a negative 3. There's that ordered pair. And when x is 2, y is way down here at a negative 9 or so. So at any rate, there is the straight line. This is a linear function that represents y equals 3 minus 6x. Now, that passes a vertical line test, it is a function, and it passes a horizontal line test. So its inverse should be a function, and we should be able to say that it and its inverse are a one-to-one. Now, what we could do is we could say that its inverse is x equals 3 minus 6y. That would be the definition of its inverse. And we would come in over here and we would say, well then, I'm going to pick values for x of 0, 1, and 2 and put them in there for y. Hopefully I said y just now. And when I do, I'll get outputs that look like this. Again, remember, an inverse relation is you have an ordered pair and they switch places. The values of the ordered pair switch places. So my first ordered pair is x is 3, y is 0. My next is x is a minus 3, y is a positive 1. So that's right here. And then x is a negative 9 way out here somewhere and a positive 2. And so I get a straight line that looks like that for its inverse. Again, I'm hoping that this is a reflection about that line where y is equal to x. And it sure as heck does look to be. You know, if I took paper and folded this, I would get a reflection across that axis. We have determined that this passes the horizontal line test and that this is a one-to-one function. I've graphed a function on the board. It's a linear equation, y equals 4 plus 7x, and I've picked some ordered pairs, or picked some values for x and found the output for y, and therefore some ordered pairs and plotted those points. Here's directions that I'm going to give to you, though. It says, determine if a function is one-to-one. So in other words, is its inverse a function as well? If it is, find a formula for its inverse, and then notice the reflection of its graph over what the line y equals x. So first of all, here's the function. From here on, what we're going to do, instead of leaving this we're going to switch values. That's what we've been doing. Step number 1 is to determine its inverse. Let this be x and let that be y. So I'll have x equals 4 plus 7y. But we state its inverse with y being alone on one side. So what I need you to do now is I need you to take this statement and subtract 4 from both sides. So I'll write this as x minus 4 equals 7y. Again, wanting to get y alone, so we'll divide both sides by 7. We might write that, and there's a couple of ways. We can just say x minus 4 over 7 equals y, or we could say x over 7 minus 4 over 7 equals y. But now what I'd like you to know is this right here is defined as the inverse function, and that's how we say it. We say the inverse function of x. That does not mean take the letter f and raise it to the negative 1 power. It is notation to represent the inverse function of this original equation, and that is x minus 4 over 7. If we were to now create a table of values, given this inverse function, and this is kind of a nasty one, these are the values I picked. I picked 4 and 11 to put in for x because they were convenient. When I put a 4 in here, 4 minus 4 is 0, and 0 divided by 7 is 0. When I put 11 in here, 11 minus 4 is 7, and 7 divided by 7 is 1. So those two ordered pairs make a straight line. They were convenient ordered pairs. So I'm going to go over here and plot the first. So there's where x is 4, y is 0. Where x is 11, y is 1 is way out here. If you'll let me just kind of estimate it, it's way, maybe right here. And that line then would be right there. That's the graph of the inverse function. And all I wanted to do, now mind you, I've sketched this. I wanted to be sure that it was a reflection over that line, and it sure does appear to be. So it looks like I have a function, and I have its inverse. This is the way I state it. I've graphed it. It passed the horizontal line test to begin with, so I was able to write the inverse function. And I've completed everything that I was asked to do, which is determine if it's a one-to-one, find the formula for its inverse, and then graph it and note its reflection across the y equals x axis. What I'd like to have you note now, we've done a lot with inverse functions, is the calculator corner in your book on page 712 shares with you how you could graph functions in their inverse using the graphing calculator. It's interesting. I think you should check that out and potentially have assigned or asked you to do that as well. Composite functions are a very interesting study, and what I'm going to do is I'm going to use the example of the shoe situation, a little bit different than I was getting at a little bit earlier. It's going to be, again, from our book, but it's going to compare my shoe size in Italy at first and I'll find out what my shoe size is there. And then I'm going to take a function that represents my shoe size in Italy as compared to Great Britain. After we've done that, then we're going to say, okay, well then what would my shoe size be in Great Britain directly from my United States shoe size? So it's an interesting concept. So let's take a look. This first equation represents my shoe size in Italian based on X, my shoe size in the United States. So I wear a size 9. So I'm going to substitute in 9 where I see X. And I have 18 plus 24. Looks like I'm going to wear a shoe size of 42 in Italy. Now knowing that, then I would put that 42 in for X here to find out my shoe size in Great Britain. So that would be 1/2 of 42 minus 14. So I've got 21 minus 14. It looks like I'd wear a size 7 in, I'm getting them confused, in Great Britain. So it would seem like I wear 42 in Italy, I wear a size 7 in Great Britain. It would seem like then I could write a new expression, h of x, which says to me that if I would just take my shoe size in the United States and subtract 2 from it, I would get my shoe size in Great Britain. That's a composite function. I have gone through this sequence, used that value, put it in this expression, and then wrote my composite function based on the outputs that I got here. Well, the way I would do that, I would find h of x, or the composite function, by taking what we call f dot g of x. And it means f of g of x. And in this case, g of x is the 2x plus 1 to 24. So right here for this, I'm going to substitute in 2x plus 24. And I want to put that into the function that represents f of x. Well, f of x is 1/2 x minus 14. And so now what I need to do is substitute this in for x. So I'll have 1/2 times 2x plus 24. And I'll do the distribution. 1/2 times 2x is 1x, and 1/2 of 24 is 12. And now I'm going to subtract that 14, and I have finally x minus 2, my composite. I have my h of x minus 2. It now allows me to take my US size and turn it into, let's call this h of x, or f dot g of x. It is the composite function. That's supposed to be a little circle, and we say f dot g of x when we talk about a composite function. It's represented by my US shoe size minus 2 will give me my shoe size in Great Britain. This is a good example of composite functions. For the most part, we're going to ask you to take equations and find their composites, both with numbers and with expressions themselves. Okay, I want to use these skills, and I want to find two things. I want to find the composite function f dot g of x, and I want to find the other composite function g dot f of x. This means, please, that you want to take f of g of x, and this means that you want to take g of f of x. Use that notation, you will, to keep that straight. And I'm going to use these two functions to find the composite function. In this case, right here, f of g of x means that I need to take the expression for g of x, 2x squared minus 5, and substitute that into f, this expression right here, into 4x plus 3. So the independent variable, if you will, in for x. So I'll have 4 times 2x squared minus 5, because I've substituted that in for x, plus this 3. I'll distribute. So here I have 8x squared, and 4 times a minus 5 is a minus 20, plus this 3, and that combines to be a minus 17, I believe. And I'm done. I have f composite g of x, or f of g of x, is equal to 8x squared minus 17. I'm going to give you a minute to copy that down, and then we'll look at the next composite function. And you can come back as well. So, if I were looking for now g of f of x, I have to substitute in to g the expression 4x plus 3, which is f of x. I have to substitute that into 2x squared minus 5. So for x, I have to put in the binomial 4x plus 3. So I have 2 times 4x plus 3, that binomial squared, minus 5. When I square that binomial, and I'm not going to write that all out, you should write it out twice to make sure you get what I get. I'm going to get 16x squared plus 24x plus 9. When I multiply that binomial times itself, bring down your minus 5. Now I have to distribute the 2 times every term. So I'll have a 32x squared plus a 48x plus a 18. And then I'm going to subtract that 5 from that 18. So finally I'll have 32x squared plus 48x plus 13. That is the composite function g dot f of x. That's all there is to it. And I could put numbers into these. I could find a value, given a 2. I could find g dot f of 2, if you will, and put it into that expression. Again, I could put any values in, like we did with the shoes. An interesting thing can be found about a function and its inverse when we talk about composition. And again, I'm going to read directly from your book about inverse functions and compositions. Suppose that we used some input, x, for the function f, and found its output, f of x. The function f to the minus 1, or its inverse function, would then take that output back to x. So if we compose a function in its inverse, we should always get x when we're done. And so the last thing that we'd like to have you do is to take a function and supposedly, what is its inverse, and take its composition in either direction and see that you get x as a result. So what I'm going to do here is I'm going to take a function and supposedly its composite, or its inverse, I'm sorry, and I'm going to find the composite of f and its inverse. And what that means again is to take f to the minus 1 of x, which is its inverse function. So my inverse function is 2x minus 7. I'm going to replace that. I want to put that in for x into my beginning function value. So for x, I'm going to put in 2x minus 7. So I'll have 2x minus 7, and then I'll put this plus 7 down, all that in the numerator, over 2. And in the numerator now, this minus 7 and plus 7 add to be 0. And 2x divided by 2 simplifies to be x. And we said that if this is truly its inverse, when we take the composite of a function and its inverse, we should get what we started with, or that value x. Now let's do this in reverse. This is f of its inverse. Let's now take, and I'll give you a minute to copy, let's take the inverse composite f of x. So let's go in the other direction, which means to take and put into the inverse function the value for f of x. And so again, let's go ahead and just get rid of all this. I want to take f of x, which is x plus 7 over 2, and I want to put that into, I'm sorry, I lost my minus 1 here. I want to put that into the inverse function, which is 2x minus 7. So where I see x here, I'm going to put in x plus 7 divided by 2. So I have 2 times x plus 7 divided by 2 minus the 7. The 2's cancel out here. And so what I have is x plus 7 minus 7, and the 7 minus 7 add to be 0. And again, I found that the composite of its inverse and the original function is equal to x. So we have proven that this is truly a function and its inverse. Now we could have done it ourselves. If this is y is equal to x plus 7 over 2, we could have, and again, remember this is often called y, we could have said x is equal to y plus 7 divided by 2, and we could have solved for y. And when we do that, that's a previous skill from earlier this section. I'll now multiply both sides by 2, so I'll have 2x equals y plus 7. I want to get y alone, so I'll subtract 7 from both sides. So I'll have 2x minus 7 equals y. That is its inverse function. That's what we checked out here. Again, this is how I would take a function and find its inverse. I took composites to see that I always get an output of x.